Insulated render systems go by many names: EIFS, ETICS, EWI, but the idea is always the same: a lightweight insulated facade that looks clean, modern and affordable. Yet behind the seamless finish lies a history of moisture failures, catastrophic fires, and design decisions that have reshaped facade engineering around the world. Today, these systems cover thousands of buildings, often with limited oversight, combustible insulation, or no fire strategy at all. My name is Eugene Korch. I teach and practice facade engineering. In this video, we'll explore how insulated render became so widespread, why it keeps failing, and what every architect and facade engineer must understand to avoid repeating past mistakes. Insulated render didn't start as an insulation system at all. Its roots go back to post-war Germany, where damaged masonry needed a new surface quickly. In 1955, Fritz Stormeister licensed an elastic synthetic render from Italian chemist Silvio Pietroboni. At that point, it was simply a flexible coating to replace brittle cement renders and hide cracks on patched bricks and concrete. No insulation, just better skin. The shift came almost a decade later. BASF had just commercialized expanded polystyrene, styropor. Stowe already had a flexible resin. Combining the two created something new: EPS boards bonded to the wall, covered with the 1955 resin render. In 1963, this became the Stowe Therm Classic. The insulation render as we know it today was born. EPS was chosen because it was light, cheap and easy to glue. Mineral wool existed at the time, but it was heavier, harder to fix, and didn't work well with the early organic renders. EPS allowed the system to be installed quickly and with minimal tools, which made it highly attractive. By the late 1960s and early 1970s, insulated render had crossed Atlantic to the United States. The Fair Housing Act created a huge demand for affordable homes, and the 1973 oil crisis made insulation a priority. A system that promised fast insulation, good thermal performance, and clean flat facades arrived at exactly the right moment. And this flat jointless surface fit neatly into the modernist aesthetic of the era. Architects wanted clean planes and continuous facades, and insulated render delivered exactly that. In the 1980s, as architecture moved from strict modernism into the more expressive postmodern period, insulated render found a new role. The same lightweight EPS and thin coating that once created flat, jointless facades now allowed architects to shape buildings in ways that heavy materials never could. Cornices, curves, frames, recesses, features that could have been expensive in concrete or stone could be cut from simple foam and coated with the render layer. But underneath those shapes, the system remained very straightforward. And understanding this structure is essential before we talk about the failures of that followed. Every insulated render facade is built from the same basic layers. First, the backing wall, originally blockwork or concrete, and later, unfortunately, the stud wall. This is the real wall, the structure, airtight layer, and fire compartment line. Second, the adhesive, a cement-based glue that bonds the insulation to the wall and evens out the surface irregularities. Third, insulation layer, most commonly EPS, expanded polystyrene, or better still, semi-rigid mineral wool insulation. It provides the thermal performance and creates the thickness needed for architectural forms. Then mechanical fixings, which were introduced later. Stainless steel anchors with plastic or steel mushroom heads that hold the insulation in place and resist the wind load. Then the base coat and mesh, a thin cementitious layer with embedded glass fiber mesh. This is the reinforced skin that prevents cracking. Then the primer and the top coat, the final decorative finish. It looks clean and uniform, but as we are about to find out, it's not the waterproofing layer. This simple build-up made insulated render fast, flexible, and inexpensive. But the simplicity also meant the system had no natural drainage, no cavity, and very little tolerance for water. And once you understand those layers, the next part of the story becomes obvious. The early systems had no way to deal with water. Through the 70s and 80s, insulated render spread rapidly in Europe and North America. It was marketed as a sealed facade, a perfect outer skin with no joint, no cavity, no drainage. The idea was simple: if the water can't get in, nothing can go wrong. But that assumption was the start of most of the industry's problems. Early insulated renders, what US called EIFS, relied on perfect joints, sealed perfectly with Perfect windows across thousands of meters of facade. That is an impossible standard. And once even a small crack formed or a window seal failed, water slipped behind the insulation. From that moment, three things went wrong at the same time. The render coat did not drain water, the EPS trapped it against the wall, and the backing wall, gypsum, OSB, timber studs, was highly moisture sensitive. Drying potential was close to zero, especially in humid climates. That's exactly what caused the leaky condo crisis in Canada and widespread failures across the US Southeast. Walls that looked perfect from the outside were rotting from the inside. By the early 90s, thousands of homes had mold, decay, delamination, or structural damage. Some states even restricted the use of EIFS walls, opting for rain screen cladding assemblies. The lesson was simple. All facades leak. If a system cannot manage water, it will fail. The failures of early barrier systems forced the industry to change. Once it became clear that the water always finds a way behind render, the system had to be redesigned around a simple principle: control the water, don't deny it. Modern systems now work very differently from the original EIFS of the 70s and 80s. First, the waterproof layer is now on the wall, not in the render. The render is a finish. The real water control layer is the membrane or coating applied to the backing wall before any insulation goes on. Second, modern insulated render includes a drainage path. Instead of gluing insulation flat on the substrate, there is a small gap or structure that allows moisture to move downwards. Even a few millimeters can make a huge difference. And on timber or steel stud walls, guidance such as NHBC requires a 25mm drainage cavity to protect the sheathing. Third, the system now expects water to leave. Drainage grooves, channels, base of wall weeps, and properly formed flashings give water a clear exit. Once you accept that the outer coat will get wet, the design becomes predictable, durable, and much safer. With these changes, water barrier on the wall, drainage behind the insulation, and the exit at the base, modern insulated render systems perform far more reliably than the early perfect barrier versions. Let's talk about how much insulation do we really need on the outside of the building. Because while external insulation works very well thermally, the performance gains don't increase in a straight line. Let's take a typical example: 150mm blockwork and add different thickness of EPS on the outside. With 50mm, the U value drops to about 0.58 watts per square meter Kelvin. A big improvement, but nowhere near today's requirements. At 150mm, performance improves dramatically to around 0.22 watts per square meter Kelvin. This is where most of the thermal benefits appear. Increase to 250mm and you reach roughly 0.13 watts per square meter Kelvin. Better, but no longer a big jump. At 350mm, you are around 0.1 watts per square meter Kelvin. And even at 500mm, the U value only reaches 0.07 watts per square meter Kelvin. Half a meter of insulation for a small reduction in heat loss. To hit a typical European target of 0.18 watts per square meter Kelvin, you normally need around 180 to 200mm of EPS or mineral wool insulation. Beyond this, the facade becomes thicker, heavier, more complex to fix, and more expensive, but the thermal improvements slow down significantly. The key point is balance. Choose the insulation thickness that meets the energy requirements without making the facade unnecessarily complicated. And for polystyrene insulation, the thickness matters for another reason too. The more combustible insulation you add, the larger the fuel load becomes. Insulated render started as a retrofit solution, and decades later, it came back to exactly that again. In the 1990s and early 2000s, thousands of modernist concrete blocks across Eastern Europe needed thermal upgrades. EPS was cheap, lightweight, and easy to fix to old facades, so it became the default choice. Sometimes whole buildings were insulated at once, other times individual flat owners added insulation to just their section of the facade. Today it's not only old buildings. New buildings, especially blockwork infill, are routinely wrapped in white or graphite EPS and finished with a thin render coat. And this is where the fire risk begins. EPS is combustible, thermally efficient, but combustible. On its own, it ignites, melts, and produces flaming droplets. Behind a non-combustible render coat, it may look safe, but real fires behave very differently from small lab tests. When exposed to strong flames, an apartment fire venting out of a window, or an e-bike battery, or even a rubbish fire, the EPS starts to melt behind the coating. Once the foam disappears, the render is no longer supported. It cracks, pieces fall away, and the molten polystyrene ignites as soon as it meets the flame. Those burning droplets fall downwards and ignite the facade below. And because the insulation has melted away, a gap opens up between the render and the backing wall. That gap acts like a chimney, pulling fire vertically through the system and spreading it quickly across the facade. This pattern has been seen repeatedly: Winnipeg, Munich, Berlin, Las Vegas, Zagreb, Dijon, and the recent drone strikes in Ukraine. In each case, the flames spread following the same sequence: melting EPS, cracking render, burning droplets, and rapid vertical fire spread within the newly created cavity. For taller buildings, the answer is straightforward. Use mineral wool. It does not burn, it does not melt, and it continues to support the render layer during a fire. Where EPS is used, typically on the low-rise buildings, fire barriers are essential. They should be installed at slab levels, around window openings, at corners, and at the base of wall. Without barriers, any local ignition can become a full facade fire. EPS itself is not a problem. Using it without a fire strategy is. Fire safety isn't the only performance area where insulated render needs careful thought. Acoustics is the other major one, especially with EPS insulation installed onto the stud walls. Sound transition is strongly influenced by mass. Heavy materials tend to block airborne noise well. Lightweight materials don't, and EPS is extremely light. When insulated render is installed over a lightweight stud wall, the whole wall assembly has very little mass. The render is thin, the EPS is light, and the studs themselves don't add much resistance to sound. So external noise, traffic, voices, impact sound can pass through more easily. The EPS isn't making things worse, but it isn't helping either. Mineral wool behaves differently. It still isn't heavy like concrete, but it has more density and better sound absorption properties than EPS. It helps damp vibration and reduce mid to high frequency noise. So the logic is straightforward. If the backing wall is blockwork or concrete, the wall already has mass. Acoustic performance will generally be acceptable with EPS, and mineral wool simply improves it further. If the backing wall is timber or steel studs, the wall is already acoustically weak. In this case, mineral wool insulation on the outside gives noticeably better performance and should always be considered. When you look back at everything we've covered, moisture, insulation, thickness, fire, and acoustics, there's one theme that sits underneath all of it. Competence matters more than the material. Insulated render is one of the cheapest facade systems on the market. And because it's cheap, it's often designed by nobody, checked by nobody, and installed by whoever happened to win the tender. On many projects, the entire facade, fire barriers, drainage, fixings, movement joints, window interfaces, is left almost entirely in the hands of the installer. We have seen the results of that approach. In Eastern Europe, flats were insulated one by one with no coordination between owners. In new mid-rise developments, EPS has been installed with no fire barriers at all. And in projects like Block 5 in Podgorica, an entire building was wrapped in EPS without a facade designer or fire engineer being involved at any stage. Insulated render itself is not the problem. The problem is using a system that relies on correct detailing, correct fixings, correct substrates, correct fire barriers, and correct drainage, without the people who know how that system is supposed to work. A safe and durable facade needs a designer, not just an installer. It needs a fire strategy, not just a test report. And it needs supervision, especially on low-cost projects where corners are easiest to cut. Most facade failures are not materials failures, they are competence failures. And that is why all insulated render case studies on facade intelligence and all relevant guidance and courses on IST are free and will remain free. Good information is the simplest, most effective tool we have to prevent the next avoidable disaster.